Moving along with our Algebra 2 review, what we're going to do here in Unit 2B1 is take a look at rational functions real quick. And this is a short unit. We're just going to hit the highlights. So what we're going to do for this part of the lesson is going to look at the rational functions, domain, vertical asymptotes, and wholes of the functions as well. Just a refresher, a rational function is a function that can be written as a fraction of two polynomials where the denominator is not zero. We can't let that be zero. Causes all kinds of problems. Dogs, cats, falling from the sky, whatever. So that would be a no-no. And hopefully this is in good standard form or factored form, but it could come in some disguises. So first thing we're going to do is we're going to look at domain. Because this can't not equal to zero, we're going to have domain restrictions on the work that we're going to do. So here's the first one. F of x is equal to 1 over x minus 4. Well, if we were to set this equal to 0, we're going to find that when x is equal to 4, we're going to have a problem because 4 minus 4 is 0. We have 1 divided by 0, and the world comes to an end. So x cannot equal to 4. So our domain restriction on this one is going to be domain for all x's such that x does not equal to 4. Okay? There we go. All right. Now, let's go ahead and look at this next one. We have a difference of two squares here. So I can factor this as 1 over x minus 3, x plus 3. And therefore, when we set each one of these terms equal to 0, we can't have x is equal to 3, and we can't have x is equal to negative 3. Those would be no-nos. So my domain will be all x's such that x doesn't equal to 3, x doesn't equal to negative 3. And you could have wrote that as plus or minus 3. Okay, next one. Let's go ahead and talk about asymptotes. One of those funny Greek words that got handed down from us. I believe it was Apollonius or somebody. And we still use the word that he basically used. And it talks basically about limits. And you were introduced to limits possibly in geometry. So if the numerator and the denominator have no common factors, so you can see factoring is going to be a big deal in rationals, then f of x will have vertical asymptotes at the zeros as a denominator. Excuse me. So here we have the reciprocal f of x is equal to 1 over x. We know that x cannot equal to 0. Okay, that's a domain restriction. And what happens is if we were to graph this, it would look sort of like this. This is the parent function of your reciprocal function, which hopefully you have memorized. At least I'd be able to identify it. So let's look at the behaviors as we approach 0 from the right and approach 0 from the left. So as we come up here and we get closer and closer to 0, it's going to come up and up and up to positive infinity. It'll never touch. And the same here, as we get closer coming from the left to 0, it's going to go to negative infinity. It will never touch. This is a behavior, but it's not an end behavior, it's a local behavior. And whenever we have a local behavior like this, we have an asymptote. And that asymptote is actually at the line x is equal to 0. And we can find these pretty quick by finding out where we have the denominator equal to 0 when it happens when the denominator is equal to 0. So all we do in this case right here is we have 1 over x plus 4. We're going to set that equal to 0, and we're going to have an asymptote at negative 4. So we know that the domain restriction is we can't have it at negative 4, but we would have a simple graph. I could draw one real quick. This sketch is probably going to go bad. But this is that parent function we just looked at shifted over left 4. So we would have a domain, I'll try and do a dash, at negative 4. Okay, x is equal to negative 4. And we would have the graph come in like this. And we would come in like this. That's all we're doing. Okay, shifted over left 4. So here we have 1 over x minus 3 and x plus 3. So we would have asymptotes at x is equal to 3. And we would have asymptotes at x minus at negative 3. So we would have our graphs, and it would look, here's 3, here's negative 3, and we would have graphs that would look rather interesting. Let's talk about holes and x and y intercepts. All right. So holes are created by common factors. Got to have the common factor, because what happens if we were to simplify this, and I went ahead and just copied this from a book somewhere, and these would cancel out because 1 over 1 is just 1, any number divided by itself. So we would just have 1 over x minus 3. Okay, and that's your parent function shifted over right 3. However, we can't have a 0 in the denominator, because if we let x equal to 2, this becomes a 0, and 0 times x minus 3 is going to equal to 0, and then we still have that massive problem. But it doesn't have an asymptote. It has what we call a hole, and it would be occurring at x is equal to 2. Sometimes we don't always know what that y-coordinate will be. We'll have a pretty good idea how close it is, but we could get some pretty interesting fractions or decimals. So what we do is we just kind of sketch the graph, and then at that point we put a hole there. All right, so let's take a look at a couple examples. So to find the hole on this, all we're going to do is we're going to go ahead and factor this. Okay, we're going to have x minus 4. Difference of 2 squares, you're going to have to get used to that. And simplified form is x minus, 1 over x plus 4. And that's going to be your parent function shifted left to 4 again. Okay. So we've seen this. But the only thing we want to do now, so we know we have an asymptote at x is equal to negative 4. So we have an asymptote at negative 4. All right, so the equation, we would capture that. We'd have domain restrictions where x can't be 4 or negative 4. And we would have a hole at x equal 4, because this got canceled out. All right. Alrighty, so let's take a look at intercepts. So right here we have x and y intercepts, and this is pretty straight. You've done this before, going all the way back to Algebra 1. X intercepts are found by setting the simplified numerator equal to 0. So simplified numerator, well, simplified numerator is just 1, so there is no x-intercept. Okay, there's nothing to set to 0. For our y-intercept, we're going to put found by setting the x equal to 0. And we can look at the original equation if we wanted to. All right, 0, that's going to be 4 over 16, which is going to be 1/4. Okay, so the y-intercept is equal to 1/4. And we write these as coordinates. There's no x-intercept, but the y-intercept would be 0, 1/4. All righty, so here we're going to take a look at a more complex problem. So what I can do is I can go ahead and go and factor difference of 2 squares on the top. And we got what times what is equal to negative 3, and that together gives negative 2. So we can easily factor that out as x plus 1 and x minus 3. All right, these cancel. This right here cancels with that. All right, that creates a hole. But our simplified rational is x minus 1 over x minus 3. So we have our asymptote of x is equal to 3. So we have an asymptote of x is equal to 3. And we have a hole at x is equal to negative 1. All right. So our x-intercept, so all we're going to do for our x-intercept is just set this right here equal to 0. All right. So we have x minus 1 is equal to 0, so x is equal to 1. So that's our x-intercept at 1, 0. And our y-intercept, we're going to put zeros in it all. Now I can put zeros up here, I can put zeros up here, I'm going to get the same answer. 0 there just gives me a 1/3. So my y-intercept is 0 and 1/3. Alrighty, I'm going to pick up with horizontal and possibly slant asymptotes on the next video.